Our next lab will involve constructing computer models of the motion of an object attached to a spring, sometimes called a spring mass system. As a warm-up for that, today we're going to discuss how to model the motion analytically, starting, as always, from a fundamental principle. Here we are interested in predicting the motion over some period of time. Our past experience with motion prediction suggests we should start with Newton's second law for this, so we will do that. Let's consider a block of mass m that sits on a frictionless table and is attached to a spring as shown. We'll choose the x-axis aligned with the spring, and the y-axis will be perpendicular to the table. The positive directions for these axes are shown. We'll choose as our origin the location of the block when the spring is at its relaxed length L0. We'll choose as our system the block, so to predict the motion, we know we need to specify the net force acting on the system. So let's identify all the agents acting on the system. First, the agents in contact are the spring and the table, with respectively a spring force and a surface contact force, which is perpendicular to the surface, since we are told that there is no friction between the block and the table. We have one agent acting at a distance, the Earth, exerting a gravitational force, the weight. Here's the free body diagram summarizing these interactions. Let's decompose the vector form of Newton's second law into two scalar equations, one along the x direction and one along the y. Now we need to imagine what the block's motion would be if we start the block out by stretching the spring and letting it go. We would expect the block to move along the x direction, but we would expect that there would be no motion along the y. Let's focus on the y direction first. No motion along y means the displacement delta y is 0, and so too delta y over delta t. The y component of the velocity is also 0. In other words, the y component of the velocity is constant, equal to 0, so that means, by Newton's second law, the total forces along the y direction must also be 0. Both the weight and the surface contact forces act only along the y direction, so we must have the sum of these forces equal 0. Knowing the magnitude of the weight force, we could solve for the contact force's magnitude. It's just going to be the mass times g, the strength of the gravitational field near the surface of the Earth. Notice here we didn't predict any motion. We observed motion along y and used that to make specific conclusions about the interactions. One caution, however, be careful not to overgeneralize here. We know that the weight and surface contact forces happen to have the same magnitude and point in the opposite directions here only because we first observed the velocity is constant along the directions that they act. And then, from this observation, Newton's second law tells us that in this specific case, that the surface contact and weight forces have the same magnitude. Now it's a different story along the x direction. There is only one agent, the spring, and one force, the spring force, acting along this direction. So if the spring is not at its natural length, that spring force is non-zero, and so too the net force along the x direction. So here we know what that force is. It's minus k, the spring constant, times x, where x is just L, the length of the spring, minus L0, the relaxed length of the spring. We know the forces here, but we don't know the motion, so we need to solve for that to predict the motion. Let's put what we know about the net force along x into Newton's second law. Now from here we could use the computer to help us predict the motion iteratively, but let's do this analytically instead here. First, we need to do some algebra to rearrange Newton's second law into this form, and then take the limit as delta t goes to 0, and so we obtain this derivative form for Newton's second law. We're going to take one more step here and use the derivative form for the x component of the velocity as dx dt. Plugging that in, we see that Newton's second law has this form for the motion of the spring mass system along the x direction. The second derivative of the x position with respect to time is equal to the x position multiplied by a negative constant, minus k over m. This is an example of a differential equation, an equation whose solution is not a number, but a function, in this case a function of time. The function that solves this equation must have the property that when the function is differentiated twice with respect to time, the result is the same function multiplied by a negative constant. The trigonometric function cosine has this property, so we'll guess a solution of this form. The constant a here is equal to the maximum stretch. So, for example, if we pull the block and release it from rest, when the length is equal to the maximum length, then a is equal to the maximum length minus the relaxed length. The constant omega we can determine by plugging this form of the solution into the equation. By differentiating twice, we end up with this expression, and we see that omega squared is the ratio of K over m, the spring stiffness divided by the mass of the block. Or equivalently, omega is equal to the square root of K over m. To get some insight into the physical meaning of a and omega, let's sketch out what the block's position predicted by this solution is as a function of time. It looks like this, which is basically a plot of the cosine function. Physically, this tells us that the block oscillates back and forth along x. That makes sense. An object attached to a spring often exhibits this motion. We see that a tells us how large in space that back and forth motion is. For this reason, a is called the amplitude. The larger the amplitude a, the larger the range in x over which the block moves. Now in time, there is a characteristic time scale over which the motion repeats itself. This time scale, often labeled capital T, is called the period. The reciprocal of the period, 1 over t, tells us how many oscillations occur in a given amount of time. This is called the frequency, and is often labeled with a lowercase f. The quantity omega is a kind of frequency, called the angular frequency. It's 2 pi times f. And we can also express omega in terms of t. Notice that this tells us something remarkable. By measuring the mass and the spring stiffness, we can predict the period and frequency of the oscillations of a spring mass system. With this in mind, give this question a try. Here's the solution. For a given spring and mass, we know the corresponding period. Now, we're told the spring stiffness doubles, meaning we can write our new period like this. Now, if we factor out the square root of 2 in the denominator, we recognize the rest of the expression is just the period t, the original period t. And so we have the new period is equal to the original period divided by the square root of 2. And so if the original period is 1 second, then the new period is 1 over the square root of 2 seconds, or approximately 0.7 seconds. That makes sense. We expect the oscillations to get faster, the period to get shorter, if the spring gets stiffer. In our upcoming lab, we'll have the opportunity to relate the physical properties of the mass and spring stiffness to the oscillation period of a spring mass system. So it's good that we now know how to do this.